Welcome to today's lecture. Today we're going to talk about private mean estimation. So through most of this class, we've focused on trying to estimate properties of a given data set. Say, estimate the mean of a data set, answer some queries on a data set, or so on. Today our focus will be, we'll start with that, but then we're going to go on to look at estimating the mean of some underlying distribution or some underlying population. This is kind of related to something I touched on during the previous lecture too, where I guess 2 lectures ago we talked about differentially private ERM, and in that we focused on trying to minimize the risk on a fixed data set. But instead, today we're going to, for the most part, we're going to focus on sort of the generalization question, trying to estimate a property of the distribution which generated that data set. So we'll start off nice and easy and go back to some of the questions we've already discussed during this class. For example, let's start with binary mean estimation. So let's say we're trying to estimate the mean of a binary data set. So we have x1 through xn, where each xi is in 0, 1. So each point is just either 0 or 1. For example, you can imagine that this is a set of n people, and each variable xi tells if individual I is male or not male. So then suppose we want to understand what fraction of the data set is male. So the true fraction of the data set that's male is something like p tilde, which is equal to 1 over n summation of xi. So this is the true estimate. However, of course, this is not differentially private, and instead we could imagine computing the following differentially private estimate of this mean. So the natural way to do that is using p hat, which is equal to 1 over n summation of xi. And we know the sensitivity of this function, since changing one point will either change it 0 to 1 or 1 to 0, the sensitivity is 1 for the summation, and therefore this rescaling by n makes it have sensitivity 1 over n. So therefore, the following is a privatization of the statistic p tilde, where you add Laplace 1 over epsilon n noise. So this is our estimator, and the question is, how much error does this incur? That is, what is the difference between p hat minus p tilde? And just by taking the difference between these two, we'll see that their difference is this Laplace random variable, Laplace with parameter 1 over epsilon n. And just using any sort of your favorite inequalities, for example, Chebyshev's inequality is the simple generic one, or you can also look at the tail probability of the Laplace random variable. But it'll say that this is less than or equal to some constant, say, times 1 over epsilon n, with high enough probability. So throughout this lecture, we're not going to really worry about what sort of probability these statements occur with, but generally everything will happen with high enough probability that it won't really be that big a deal if you just set all the constants right. So to kind of hide the details, we're going to kind of ignore these sort of with high probability type guarantees. So yeah, this says essentially that the error between the non-private estimate of the mean of the dataset and the privatized estimate of the mean of the dataset is 1 over epsilon n. And in particular, let's suppose if we wanted accuracy alpha, then we would need 1 over epsilon n to be less than or equal to alpha, which requires n to be greater than or equal to 1 over alpha epsilon. Okay, so that's sort of the very most basic question in differential privacy in some sense. On the other hand, like I said, we're going to this kind of like estimating some data set mean. Let's instead move to the statistical setting. So imagine now that we have again some data set which is binary, but we don't really care about estimating the mean in particular of this binary distribution, this binary data set. Instead, we have some underlying distribution which we want to be estimating the mean of. So this time, suppose that, let's draw a line here. So let's suppose that x1 through xn is generated IID, so independent and identically distributed from Bernoulli with some parameter p, where p is unknown, and that's essentially what we want to estimate. Yeah, so p is some parameter between 0 and 1, so just the probability that a coin comes up heads. So just to continue our sort of analogy, this could be, this is how many people in a data set are male, but this could be if you sample a data set from some underlying population, some underlying distribution, what fraction of humans, say, in the world are male? Okay, so let's try to understand, this data set. What can we say about it? So the first thing we can say about each xi is that it's going to be the expectation of xi is equal to p, and also by kind of linearity of expectation, that tells you that if we just look at expectation of the sum of xi's, this is also equal to p. So this is just a basic property of a Bernoulli random variable. Let's also look at the variance of xi. So the variance of xi, again, this isn't a hard calculation to do, but it's p times 1 minus p. Using this fact, what can we say about the variance of the empirical average? Well, this is equal to, if you're familiar with this sort of thing, like what'll happen is if you pull out this, well, let's just do this out, I guess. When you pull out the constant, it becomes squared, so you have 1 over n squared. And then since you have a summation, or let me write this out step by step. Variance of summation of xi, and then variance is linear when the summands are independent, so this just becomes 1 over n squared times n times variance of xi. And the variance of this is just p times 1 minus p. So this is just overall equal to p times 1 minus p is over n. And you can see that if you can upper bound this actually by 1 over 4n, because this is sort of maximized at the value when p is equal to 1/2. So okay, good. We have now, if we're looking at this random variable, 1 over n times summation of xi's, we have mean and we have an expectation for that. So therefore, using Chebyshev's inequality, we have that, essentially recall that, we'll just write this out, I guess. Chebyshev's inequality says that p minus p tilde is less than or equal to O of 1 over square root n with sort of high enough probability. So I'll just leave out that with high probability statement. And recall that p tilde is sort of the empirical mean, and this is the true mean of the distribution. How did we do this? I mean, right, it's just saying, like, looking at the standard deviation of this distribution, looking at the standard deviation of p tilde, which is 1 over, recall that p tilde is 1 over n summation of xi. The standard deviation of that is roughly 1 over square root n, and Chebyshev's inequality tells you that a random variable is going to be a constant number of standard deviations away from its mean. So that's why it's going to be O of 1 over square root n distance away. Okay, this is nothing about privacy. This just tells you that what the difference between the true mean of the distribution and the mean of the data set is going to be. But we also know something about how much error we get between the privatized mean and the mean of the data set, which is 1 over epsilon n. So therefore, if you compute the error introduced due to the sampling step, that is how much difference there is between the true parameter and the empirical mean, and then you compute the difference between the empirical mean and the privatized mean, then we have the following. Let's just write it out with full detail. So we have that p minus, we want to compute what the difference between p and p hat is. So recall this right here is the true mean, and this is the privatized estimate of the mean. Well, we can just bound this by triangle inequality. This plus p tilde plus p hat. And this is going to be, by the previous calculation we did up here, 1 over, sorry, this is this one right here actually. This is O of 1 over square root n. And then the other term here is going to be O of 1 over epsilon n. So right here, this is our sort of rate, as it's called, the error between the true parameter and the privatized estimate of that parameter. So you can see that we have 1 over square root n plus 1 over epsilon n. Now, this is what's known often as a rate in terms of the accuracy, the error. But another way of sometimes doing it is asking the following question. If our goal is having alpha error, then what condition do we need on n? How big do we need n to be? And so this is fairly easy to convert between this representation and this representation. In particular, you can just say, okay, if we want 1 over square root n plus 1 over epsilon n to be less than or equal to alpha, then what condition do we need on n? Well, this will imply that if you just sort of see what it takes, this means that we require that n is greater than or equal to O of, say, 1 over alpha squared plus 1 over alpha epsilon. Right, so that's the sample complexity of this problem, how many samples from the distribution we need in order to get accuracy alpha. So you can see here that, well, what is the cost here? Well, let me point out that this cost here, this 1 over square root n or this 1 over alpha squared, these are both the non-private cost. And this new cost here is 1 over alpha epsilon or 1 over epsilon n. This is the cost of privacy. So this is the question I always like to ask whenever solving a problem like this. What is the additional cost due to privacy? And we can see here that the additional cost due to privacy is 1 over alpha epsilon. Now, is this a large cost of privacy or is it a small cost of privacy? Well, I consider this to be not too bad. It's going to be noticeable, definitely, but it's a relatively low cost of privacy because why? Well, often we think of, remember, epsilon being a constant, and alpha will be something that's like less than 1. So therefore, if you just ignore this term because it's going to be, say, 1, then this term is going to be a quadratically lower order term compared to this term. So this is, this is ignoring sort of constant factors, which are quite important in practice, but it can still be, this is still at least a good rule of thumb, showing that sort of privacy isn't too bad here. This in comparison to some cases where you might incur a dimension-dependent factor, which was not there previously. So let me just kind of summarize kind of how we did this analysis. Let me write out a little bit of the analysis because this is going to be useful later. So what we want to do is compute the distance between, let me write it as we did before, p minus the sort of average of the points plus noise. So I'm going to use this term here, this n, to represent the noise added due to privacy. And so this can be upper bounded by the following. This is at most the difference between p minus the summation of the xi's plus the difference between 1 over n summation of xi minus this term here. So yeah, we sort of decomposed it, the overall error. This is the error between the true parameter and our privatized estimate. We decomposed it into two terms. So this term here is the sampling error, as we call it. This is sort of the cost, the error we incur in even in the non-private private setting. So the sampling error. And then this here, you can see if you take the difference, it just becomes the added noise. But we're really taking the difference between the non-private estimate and the privatized estimate. And that gives us the noise error, I guess, or the privacy error. I don't know, whatever you want to call it. So this kind of breakdown is kind of convenient for understanding the cost of privacy sometimes, just because Yeah, we'll see it later. In fact, giving you spoilers, skipping a bit ahead, there's even a third term which we'll see sometimes, like the bias that's sometimes introduced. And we can break it down into those three terms and see how they interact with each other and how we can maybe reduce one term or increase another term in order to minimize our overall error. Okay, so this was nice. This was nice and convenient because of the fact that, everything like from sort of step one, it was convenient because we had that the points were either 0 or 1. This was immediately a bounded sensitivity statistic, but that goes out the window when we have unbounded data. So when we have unbounded data, this could be more of a problem because statistics won't naturally be nicely bounded. Yeah, above we would rely crucially on the data either being binary or at least having a bounded range, but this isn't always going to be the case. Suppose, like, let's return to, I guess, for now, the data set setting, where we have our set x1 through xn, where each xi is in R. So everything is just a real number. So to give you an example, which is, I think, a natural one, what if we we had a set of heights? So let's say human heights. Right, so we have a bunch of heights and we want to estimate the average height. Note, of course, that this is not binary data, but it's still a natural query we might want to ask about a data set. Yeah, so let's again use the same notation that we did before. P tilde is equal to 1 over n. Well, let's call it, in fact, because now it's not just a parameter p, because it's non-binary. Let's say mu tilde is equal to 1 over n summation of xi. That is the empirical average. But what is the sensitivity of this data set? Or sorry, the sensitivity is a statistic. Well, you can see with unbounded data that the sensitivity is potentially infinite. Let's just sketch this out. So imagine, here's our heights, and I don't know, they may be centered around something like, I'm not sure. I'm just taking a guess here, something around like 160 centimeters, maybe. And so, we have maybe, if we do this as a little like histogram type of representation, maybe we have like, I don't know, 150. Maybe it's going to be like the mean height is somewhere like 170, and 190 is over here, and so on. But the idea is maybe we have like a few people who are this tall, and then more people who are this tall, more people who are this tall, and so on, and so on, etc. The issue here is that why does it have an unbounded sensitivity? Well, what could happen is a single point could be taken from here. So, this point, let's say this individual is removed. And in exchange, we have an addition of an individual way over here. So imagine we have one individual whose height is recorded as, 10,000 centimeters. So you can see that this would totally ruin your empirical mean. Yeah, what I mean to say is that this statistic is very sensitive because moving one individual height from, say, 150 centimeters to 10,000 or even 100,000 centimeters to make it even more extreme, this would dramatically and potentially infinitely change your average height in the data set. So yeah, this is kind of the first issue, the fact that we have an unbounded sensitivity, and in particular, you couldn't really add Laplace noise with any sort of finite standard deviation or finite parameter, scale parameter, in order to privatize the statistic. In fact, it's possible to say something even stronger than that. It's possible to say that, in fact, not just the Laplace mechanism fails here. Actually, there's no finite sample differentially private algorithm which could estimate the mean of this data set to sub-infinite accuracy. This is because of the fact, at least if you work in pure differential privacy, yeah, this is formalizable via a packing argument, just arguing that, there's many different data sets, there's infinitely many different data sets which can have infinitely different many different possible means, and therefore you can't do anything. So This is an issue. Like, this is kind of not satisfying, right? Because we had some data set, we want to estimate the mean of it, and I'm just telling you, no, you can't, because the sensitivity is infinite and no algorithm can make it finite. That's not at all satisfying, because, you know, how would we solve any problem that we want with differential privacy? And so the answer is, this isn't the end of the road, and in fact there's something we can use other information in order to do better. Yeah, in particular, this is kind of a ridiculous example. Like, you might immediately think that this is crazy, right? We have some gross outlier here. No human is going to be 100,000 centimeters tall. And so maybe you can do something that does better than that, if there's something you can do to avoid these kind of silly cases. And the answer is yes, because really what you can do is use some a priori information you know about your data set. So for example, what we can say about human heights is that humans are between, like, humans' height. This is going to be greater than or equal to 0 centimeters, let's say, of course, but it's also going to be less than or equal to, say, 300 centimeters. I think the tallest human who ever existed was less than 300 centimeters. So yeah, the point is, overall, you know, there's some bounds in this case we can say on where our data will lie, and we can say that without looking at a single data point. Of course, you know, I could just look at the data set, see, oh, this person who's 100,000 centimeters tall, that's ridiculous, you know, that's not valid. But that wouldn't be differentially private. It would be very, like, specific based on the data set I see. So instead, what I have to do before I even start is use the fact that of information that I already know. Say, all right, I know no human heights are outside this range, so that'll be okay. Yeah, and if we do this, then in fact we can now use the Laplace mechanism using the following sort of simple three-step process. So, well, two-step process, I guess, I don't know. The point is, what you can do is, the first step is clip all data to, like, given range. So what do I mean by clip your data? It means that if there's points which are outside this range, clip it to the nearest point. So for example, in this case, where you have, say, one data point which is at 100,000, and say this is 300, then what you would do is clip it and, like, get rid of this point and move it over here and move it to this. Right. The idea here is that once you do this, then you can consider the statistic, which is the empirical mean. You can just compute summation of 1 over n xi, and we're going to use the function. We're going to let f be the function which maps to this range. And this will be sort of convenient later, you'll see. But essentially, we're going to compute f on xi of every point, and then you add on Laplace noise of magnitude 300 over epsilon n. I mean, it's a lot of noise still, 300, but it's better than an infinite amount of noise. So right, here, let me just remind you, and just to be clear, like, f of xi is the function is equal to 0 if xi is less than 0, 300 if xi is greater than 300, and xi otherwise. So it just kind of truncates it to this range. Cool. So hopefully that's clear. The idea here is that we used a priori information we had in order to put our data set in a more reasonable range, a more reasonable interval. And then based on that reasonable interval, which is hopefully bounded, then we can just apply the Laplace mechanism exactly as we did before. Okay, so this is the kind of example on how we get around this issue of unbounded data. Let's try to apply these types of ideas or these types of restrictions in order to do private parameter estimation for distributions. So this is the next thing, private parameter estimation. We talked about this very briefly at the beginning when we were estimating the mean of a Bernoulli, but let's be a bit more precise as to precisely what private parameter estimation of a distribution is. Let me just add that of a distribution. And yeah, once we state our desiderata, then we can see what we can show in the setting. So what is the setting? We have x1 through xn, and we want the following two things. So the first thing we want, of course, is privacy. That is, we want an algorithm. So we want an algorithm M, let's say, which takes in the whole data set X to satisfy following. First of all, we want privacy, of course, that we want M is, say, epsilon dp, though we might, let's just say epsilon is dp. We might sometimes later want to move from pure dp to approximate dp. And the second thing is we want it to be accurate, where we say if x, like the x being the whole data set, was sampled IID from, say, some distribution P with appropriate properties, then we have that the algorithm is accurate, where accurate can be sort of domain dependent. Yeah, in particular, for most of today, we're going to say that the output of the algorithm is close to the true mean. That's kind of the underlying goal. So, okay, these are two desires, privacy and accuracy. Let me just comment that these are two different, they're guarantees which happen at different times. The first one is a worst case guarantee. That is, we want the algorithm to be private in the worst case. And this is kind of like, even if the dataset X came up with exponentially low or even zero probability under whatever distribution P is, even if it's super, super unlikely or it shouldn't happen at all, then we still want to be differentially private. This is kind of a philosophical reason for this. The reason is kind of, well, there's multiple reasons. One reason is because, from a philosophical perspective, as a data analyst, we don't want a sort of average case privacy. We want worst case privacy instead of average case privacy, because of the fact that if we're incorrect about our assumptions about the data, we don't want the user's privacy to be violated. On another more technical note, I'll comment that if we instead had an average case differential privacy guarantee, this would result in the loss of many nice properties when we move to average case definition of privacy. And I'll refer you in the notes to some blog posts by Thomas Steinke and John Ullman. Okay, so that's privacy. It really has to be worst case. But on the other hand, the accuracy guarantee is average case or stochastic in nature. So we say that we want the data set, if in fact the data set is generated according to some distribution class or from some distribution with appropriate properties, then we want the algorithm to be accurate, say, with high probability. It's not with probability 1 necessarily, but with high probability at least. Right, and so yeah, this is a worst case guarantee for privacy, but average case for accuracy. And this is necessary even in the, you might think it might be limiting that we need some appropriate properties for the unknown distribution, but this is kind of necessary. For example, just to give you an idea, even in the non-private setting, sometimes if you want to estimate the mean of a data set, you have to assume that it has properties such as, say, a bounded second moment. For example, if you just take a set of samples from a Gaussian and take their average, then that'll converge nicely to the true mean. On the other hand, if you weren't actually receiving samples from a Gaussian distribution, you're actually receiving them from a Cauchy distribution, well, this empirical mean would not converge to the true mean of the distribution. In fact, the Cauchy distribution doesn't even have a mean. But the point I'm trying to get at here is that really, yeah, you need some sort of assumptions if you want your algorithm to be accurate. So hopefully that's clear. Those are our two things. Privacy and accuracy are the two things on the table today. Right, so with that out of the way, with the setting clear, let's get into our first algorithms. In fact, most of the class today, we're going to focus on doing private estimation of a univariate Gaussian mean. So, for example, like this might be a reasonable setting in which to consider this, height distribution question. Heights are probably going to follow a nice Gaussian distribution for the most part. The difference is here, before we were considering, say, the average height of an individual in the data set, but now we're going to consider the average height of an individual from the underlying population. Say, what you can imagine is you were looking at all humans, and you're trying to estimate what is the average human height overall. And so one way to do this is sampling to get a finite data set and then estimating what the average height is on that data set. So let's particularly try to pin down what exactly the setting is. So we have x1 through xn, and we want an algorithm which is epsilon dp on this data set. This is kind of our privacy guarantee. And in terms of accuracy, we want the following. We want it that if x1 through xn are generated IID from n, say, mu1, so there's some Gaussian with unknown mean, but variance 1, then, and also we have that the mu is less than or equal, the size of the mean is less than or equal to r, then we want to estimate the mean with high probability. So this might seem like kind of familiar. The one sort of glaring oddity here is the fact that we have this additional condition here that, say, the size of the mu is less than or equal to r. And why do we have this? Well, it's kind of the same sort of thing as we were doing before. Before we had the restriction that our data was going to be between whatever and whatever. Well, here we have that the size of the mean is going to be bounded by capital R. And this is just some parameter which is given as input to the algorithm. Like I said, we kind of need some sort of bound R, otherwise we will get an infinite sample complexity just due to packing lower bounds. And that would preclude any finite sample algorithm. In particular, we'll see that later that the right bound for this problem actually depends on the parameter R, however big it is. Okay, so what we have is there's samples from an unknown distribution, and the mean of that distribution is bounded. We want to estimate the mean of that underlying distribution. So just to relate this to the setting we were looking at before, note that a bound on the mean does not immediately imply a bound on the magnitude of the data points. However, a bound on the mean plus the fact that it comes from a Gaussian, those two together will give us a bound on how big the data points will be. So let me just make a claim here, which I'll prove for you real quick. It's not too hard. So the claim is kind of with high probability. If we draw x1 through xn, x1 through xn will all be in the range mu minus, say, O of square root log n, and mu plus O of square root log n. So I'm saying that all the data points will lie in some narrow interval which is fairly close to the mean. In particular, this square root log n is going to be a pretty small number, even for fairly large n. For example, you can see that, like, if you consider Gaussian, then if you consider Gaussian like this, then if you take this to be equal to 3, for example, then this interval will contain 99.7% of the data points. So really, like, I write this in this fancy way, but that's just to be totally precise, even for larger sample sizes. If this is confusing to you, every time I write square root log n, you can really think of this overall O of square root log n as, say, like 3 or 5 or 10 or 20 even, if you want to be very generous. That'll almost certainly contain all the points. So yeah, the claim I want to make here is the fact that if you draw n samples from a Gaussian, then all of them will lie in this interval sort of with high probability. And this is not hard to see using the following Gaussian tail bound. So if you draw a single point from Gaussian mu 1, then the probability that the distance from the mean is greater than, say, t is going to be less than or equal to this. So this is a standard Gaussian tail bound, which just says no point from a Gaussian, if you take a sample from a Gaussian, it won't land too far away from its mean. So in particular, what if we set that t is equal to, say, I don't know, just putting a sort of arbitrary constant here, set t equals to 20, square root of 20 log n, then it means that this term here will be less than or equal to, say, 2 over n to the 10, which is a tiny probability, especially for n larger than some like modest numbers. So by a union bound, that is, this is just for a single sample, but if you want the probability that none of these n samples fall in this range, or sorry, none of these n samples fall outside of this range, then just summing this, multiplying this by n will give you the desired bound. It's going to be less than or equal to 2 over n to the 9. And so that's the proof of this like little claim here, I guess. So yeah, this is nice. It says that all of the points are going to be within this range with sort of very high probability. The fit probability failure is only like 2 over n to the 9. And a corollary is that a very simple corollary. We just want to use the fact that also the mean has magnitude less than r. That means we can say all the points are going to be in a slightly larger range, but based on the value of r. They're all going to be in minus r minus O of square root log n and r plus O of square root log n. So that's an easy corollary of this. This is going to happen with high probability. So all of the approaches we described today will crucially use this fact that the data set all lies within this interval and then nothing lies outside of it. So for the remainder of this segment, I'm going to describe a very simple private estimator of the mean, which gets the wrong sample complexity, but it's at least a nice starting point, which is going to give us something to go off of. So yeah, we'll call this the naive approach. And it kind of works as, let me state the guarantees. The theorem is this kind of going to be the naive approach. So there's a epsilon dp algo, which estimates the mean of n mu 1, where mu is like less than or equal to some parameter r. And to accuracy or error, whatever you want to call it, to accuracy alpha, given n equals, say, O tilde of 1 over alpha squared plus r over alpha epsilon samples. So if you have this much data, then you can estimate the mean of the distribution up to accuracy alpha. So, okay, let's just compare this with the type of sample complexity we had before. Recall when we were doing just a Bernoulli mean estimation, then the sample complexity was 1 over alpha squared plus 1 over alpha epsilon. So you can see this is pretty close to what we have here, the one crucial difference being this r term here. So we kind of have to pay something which is linear in the range. So yeah, that's what we have for now, and let's prove this, and then we'll do some discussion of this fact. So let's see how to prove this. The proof will be just by defining a very simple algorithm, which is very similar to what we actually described. I described it to you before, rather, when we were doing this example, essentially where we clip all data to the range and then we compute a noisy mean after clipping it. But let's write it down and try to analyze it in sort of this slightly more precise setting. So, okay, like I said, the algorithm will be the following. We clip the data set to the range minus r minus o of square root log n and r plus o of square root log n. So recall, clipping the data set just means that if it's outside of this interval, then we move it to be at the endpoint of this interval. And the second thing we do is we compute the following quantity. We compute the following quantity, which is, we essentially output the mu hat, our estimate of the mean, which is 1 over n summation xi, so the empirical mean of the clipped data set. So these are the, let's clarify that these are the clipped points, plus Laplace of, say, this will be of 2r plus o of square root log n divided by n times epsilon. In fact, let's use the same notation we did before, where I used the function f in order to indicate that this is the clipping function. So f of xi is going to be the clipped version of the point. Cool. So, right. This shows that let's this is the algorithm, and let's analyze it. So the first thing that's easy to see is that this will be epsilon differentially private. Why is that? Well, the clipping step, this will limit the amount that any single point can influence the mean down to, say, 2r plus, say, o of square root log n, just because of the fact that, if you move one point from one endpoint of the interval or to the other point, the endpoint of the interval, then that's the most it'll change by. And if you put it outside of the interval, it'll automatically be clipped to this, and therefore it can't change any more than that. So the sensitivity is that quantity, the width of the interval, divided by n because we're normalizing it, and divided by epsilon to make the standard deviation for the Laplace noise. So yeah, it's easy to see that this is epsilon dp. Now let's reason about the accuracy of this procedure. So there's two things we have to, like, how do we do this? The first thing we're going to do is reason as before, or just basically as we reasoned before. The claim is that clipping won't change any points. And why is that? Well, like we said, this clipping, we said that all the data set will fall into this interval with a very high probability, and and therefore now the clipping operation won't do anything because it only affects points which don't fall in this range. In fact, this will be sort of the case for the entire lecture until we get to the very end, where we're going to have cases where we do slightly more aggressive clipping. But at least for now, this clipping won't move any data points. And so therefore, we can sort of say that, this empirical, this quantity is the equivalent of 1 over n times summation of xi's. So, okay, let's quantify the non-private error, first of all. So the difference between mu, which is the true mean, minus mu tilde, which is the empirical mean, non-private. This is going to be less than or equal to O of 1 over square root n. We can analyze this exactly as we did before, just by using the fact that this is, just by using the Chebyshev's bound or whatever you want. This is very easy to do. It's like the same type of analysis as we did before, slightly different for Gaussians, but yeah, the expectation of each xi is going to be equal to the true mean. The variance of each point is equal to 1, and therefore, yeah, just use Chebyshev's inequality and you're done. As for the additional error due to privacy, we have the following, mu tilde minus mu hat. This is going to be equal, in fact, to the magnitude of this Laplace random variable of magnitude 2r plus of square root log n over epsilon, n epsilon rather. And the magnitude of this is, like, again, by Chebyshev's inequality, the standard deviation, and kind of taking, by a reasonable bound, this should be like roughly O tilde of, sorry, yeah, this will always be O tilde of r over n epsilon, where this tilde ignores logarithmic factors because they're kind of considered lower order terms. So, okay, this gives us two things that we can put together, and just combining them simply is that the true mean minus the estimate of the mean is going to be less than or equal to O of 1 over square root n plus, let me just put this here, r over n epsilon. And therefore, if we want this to be less than or equal to alpha, let's say, yeah, we want accuracy alpha, remember, then just setting this term over here less than or equal to alpha, this implies that we need n to be greater than or equal to O tilde of 1 over alpha squared plus r over alpha epsilon, where this is exactly the statement we were trying to show, right? Just going back to the theorem statement, we have 1 over alpha squared plus r over alpha epsilon. So this is exactly the statement we have here. So let's reflect a bit on what we just showed here. So let's see how what we exactly bounded here. Like, I want to break down the error similar to how we did before. In particular, we had mu minus the empirical mean plus noise. Right, so this is what we were trying to bound, the difference between the true mean and the clipped empirical average plus noise. Well, we can bound this just using the triangle inequality and sort of breaking it down into its components. First of all, the difference between the true mean and the empirical mean. Then plus the difference between the empirical mean and the empirical mean after doing this clipping operation. And then plus the difference between the clipped empirical mean and the noised clipped empirical mean. So yeah, this might seem a little bit tedious, but you can verify that by triangle inequality, this is a valid inequality. And I broke it up into these three pieces because they represent three different sources of error. This error right here is the sort of sampling error. This tells you the totally non-private error. This is the sampling error. The last term is the privacy due to noise error. This is the noise error, let's say. The middle term is kind of new here. And in fact, it's kind of uninteresting even for now. So this is the error introduced due to bias. That is, when we do this clipping operation, how much does it bias the procedure? So let's see what each of these costs were. Well, the sampling error we kind of bounded right here when we said it's O of 1 over square root n. The error due to noise is what we bounded right here. This is going to be something like O tilde of r over n epsilon. But the one different thing is the bias. This is sort of new from before. And the way we did it was that we did this clipping threshold just so that it with high probability wouldn't actually clip any of the points. So this error is going to be 0, not to be confused with these O's. And this is only with high probability, let's say. But yeah, we have kind of zero error incurred due to the bias of the estimators. So yeah, again, this is not interesting now, the bias, but it'll become more relevant later. But that's sort of how we did the analysis. We broke it down into the error due to different sources, and we just computed how big the error was. This will be useful later. Okay, so let's recap and just sort of reflect on what we just proved. We proved the following theorem, that there's a private algorithm to estimate the mean of a Gaussian with sort of bounded mean bounded above by R. And the sample complexity was 1 over alpha squared plus R over alpha epsilon. So is this a good theorem or not? Well, it's okay. The reason I say it's okay is because, if R is fairly small, then this is just going to be exactly the cost of doing, just estimating a Bernoulli, which was 1 over alpha squared plus 1 over alpha epsilon. So that's nice, but the issue is, however, when R becomes very large. If R is very large, then this could be easily the dominating term, which would introduce a lot more noise than you would need in the non-private setting, which is kind of what we're trying to avoid. So what do we mean by this? What is sort of the noise, how should we interpret this parameter R? We can interpret this as sort of a estimate on where our data lies. For example, when we're doing human heights, we said all humans are between 0 and 300 centimeters, so R would be something like 150 if you center it right. However, you could imagine we come up with a somewhat better, estimate. Say, if we had that maybe all humans are somewhere between, at least the vast majority of adult humans are going to be between, say, 140 centimeters and 200 centimeters, then this is significantly smaller R of just 30. On the other hand, maybe we're not dealing, so that would be better here just because it would result in a better sample complexity. On the other hand, maybe we're not dealing with height, something which is so familiar to us. Maybe we're dealing with some obscure quantity for some uninterpretable regression that we're performing. In those types of cases, then maybe we don't have any sort of guess of where the data lies. Maybe we have to use exceptionally loose bounds. We just have to set R to be equal to 1,000,000 or something. In those cases, this would be an absolutely terrible bound because, the noise would overwhelm any sort of signal that we have there. So really the question is, how do we deal with the fact that this R here it can be kind of bad in some cases, and we're going to conclude the first segment right now, but the thing that we're going to try to do is see a better algorithm. In fact, I'm going to provide you with 2 different algorithms which reduce this dependence from R to, you'll have to come to the next part to find out.